All right, so like I said, we're going to start on page 28, and we'll go to page 29, then we'll swing back and grab some of those other problems. Looking at, I'm trying to remember where I wanted to start. Well, you know what? We'll do the half angle identities for cosine and sine. All right, we haven't really touched on those, so I'm going to go back, show you where you can find those. That's all back on page 23, functions of the half angle. So that's this set of formulas here. For this topic, that page we were just on, I think it's page 28. We're not we won't bother with the tangent stuff. I just kind of made an executive decision. I didn't put those kind of problems on the test, so or at least tangent. So it's not anything that you would need to really worry about, at least not for now. We'll pick it up in the next unit. I just don't want to take too much time. But these two formulas you'll need, this one and this one. So we'll start off with well, the first example. That would be cosine of 105 using a half angle identity. All right, you're going to get an equivalent answer, but it's going to have a different look to it. So if I want to represent cosine of 105 degrees using a half angle, what that tells me is that 105 degrees has to be equal to 1/2 A. All right, so you do that off on the side. I'll just throw it in over here. 1/2 A is equal to 105 degrees. All right, so that means A has to be 210 degrees. And I just kind of look at it like, you know, oftentimes you don't even need an equation. You just kind of say, well, I want a result in a 105. So in order for that to happen, A would have to be double that number because we're cutting A in half. All right. So this would become cosine of 1/2 times 210 degrees. All right. Now the formula, and actually I should have given a little bit more room here. Let me just move that down for a second. The formula is plus or minus the square root of 1 plus cosine A over 2. All right. So again, we just get that from the from page 23. All right. So if I have determined that A is equal to 210 degrees, then I could just run through this formula with a 210 replacing the A. All right. There will be the question of it says plus or minus. It's actually the either or plus or minus. It's not both, like if you're taking the square root of a number, you know, like in the context of completing the square, we always put the plus or minus. In fact, it was always like, don't forget the plus or minus, and kind of gets ingrained in your existence. But here we reference ASTC. We look at the original angle. The original angle was 105. 105 would plot in this quadrant where only sine is positive, right? We're looking at a cosine function, right? So we're looking at a cosine function in the second quadrant, which means the result must be negative, all right? So we would essentially just drop the positive and go with the negative. Then we'll find 1 plus cosine of 210 degrees over 2. Based off of unit circle knowledge, cosine of 210 degrees is negative radical 3 over 2. Ooh, give my denominator of 2 a little extra flair. I don't know. I don't want to make the other 2's feel bad about themselves, so I'm going to trim that down a little bit. All right. So this would be an expression that's equivalent to the cosine of 105 degrees. All right. not going to ask you to simplify it. You would just leave it like this. Right? It involves what we call a nested radical, a radical within a radical. There are methods to simplify that, but all it's going to get you is this, which we could have gotten using a different technique. This kind of problem is really just to practice the concept of the half angle identity. And again, it wasn't like 1 plus cosine 2tan over 2, then a miracle happened and it became negative radical 3 over 2. That's all from the unit circle, and it's been a while. Scrolling. There we go. 210 degrees. Just so happens I highlighted it when we went over this. We must have done a problem that was related to it. Negative radical 3 over 2. It comes right from the unit circle. Oh, interesting. I mean, not the end of the world, but that was strange. All right, so we want to be able to verify our answer. Now, in the NumWorks calculator, we can type in cosine of 105. Just make sure you're in degree mode. It gives you that decimal, which is equivalent to this ratio. But I want to verify it against this. Sometimes if you hit the right arrow, see those 3 dots, it can present you with alternate forms. So you might be able to get a sense. In this case, it doesn't. It just gives you a nice picture of where it falls on the unit circle, which I think is kind of cool. Although, oh yeah, it is 105 degrees. Yeah, that's where it would fall in the unit circle. So that's good. Gives you the radian form. It's kind of nice too. But it doesn't give us this. So instead of relying on the calculator to present us an answer in this form, we'll just put our answer in this form into the calculator and verify that it matches the decimal. All right, so I'm going to create a fraction, 1 plus another fraction, negative rad 3 over 2, all over 2. You could make it 1 minus positive radical 3 over 2 if you want. I don't think it really saves much in terms of effort. And just make sure that this is equivalent to the previous answer. And it is, so we're good. All right, so the result isn't very pleasant to look at, but it's still right. It's not simplified. So, I mean, we weren't asked to simplify, so who cares, you know? So so this is good enough. Now for the next one, sine of 75, it's the same idea. Sine of 75 degrees. Our sine formula, sine of 1/2 a, is about the same as the cosine 1/2 a formula. The exception is there's a 1 minus on the top of the fraction. Procedurally, we're going to do the same thing. All right, we're going to figure out the a value. So we just take this number and double it. So sine of 1/2 times 150 degrees. Based off of ASTC, and the fact that 75 degrees is in the first quadrant where all trig functions are positive, I would go with the positive variation of this formula, which means I could just write it without a sign in front. All right, 1 minus cosine 150 degrees moving stuff over a schmidgy, all over 2. And then I just make my substitution for cosine of 150. All right, cosine of 150 is rad 3 over 2. Sorry, negative rad 3 over 2. And we get that from the unit circle. Now, you see the double negative there. You kind of feel obligated to make that a positive. I leave that up to you. All right. So sine of 75. Oops, where'd the sine go? Somewhere. Sine 75 is equivalent to that. And by the way, that's what we got when we did it the other way. I want to see if this fraction, this radical expression, is going to yield the same thing. So radical 1, I'll do plus. Radical 3 over 2 all over 2, and see that it gives the same thing. And also, a really good attribute of the NumWorks calculator is that it does simplify radicals for you, right? Even more complicated ones. Which I'm sure an algebra teacher wouldn't really be thrilled about. This is an algebra, so we're good. All right, and like I said, we're just gonna we'll hold off on this topic until the next unit, until unit 3. So, and one of the reasons why is because when we work with some of the applications of trig functions, tangent tends to kind of emerge as more prominent than sines and cosines. Not always, but it just seems like a great deal more of the problems that we'll tackle involve knowledge of tangent function. All right. So we're going to learn how to solve trig equations. And an element of solving trig equations has to do with trig identities, being able to simplify it in such a way that you can clean it up and get a nice, simple equation to solve. And then from there, just solve it. All right. So the directions here, solve each equation on the interval of 0 to 2 pi. All right. So every one of them is going to say solve on the interval. Well, every one of these problems will say solve on the interval of 0 to 2 pi. If it said something like solve on 0 to pi, I would just disregard any answer I get that's greater than pi. Right? We just structure it around the domain. There's algebraic approaches, graphical approaches, tabular approaches. So we're going to focus on the algebraic for now, and then I'll show you how to do some stuff on the calculator related to it. All right. So when you're solving an equation, you want to isolate the variable. In this case, the variable is theta. All right. Treat the theta like an x. All right. What do? We get every instance of that variable over to the same side of the equation. Then we just try to get it alone by subtracting, adding, multiplying, dividing, all that good stuff, all the 4 basic operations. All right. So I'm going to subtract 4 sine theta from both sides. Cancels on the right. On the left, we're only subtracting the coefficients. So -2 sine theta plus 5 is equal to 6. You could also have subtracted 2 sine theta from both sides, bring the variable over to the right. That's fine. Even though we're not going to touch inequalities, trigonometric inequalities in this unit, I just find that having the variable on the left-hand side, not necessarily throughout the whole process, but in the final step, instead of like 2 equals x, we say x equals 2, just because if it were an inequality, it might be trickier to figure out where or the direction of the inequality, whether it should be a less than or greater than, less than or equal, greater than or equal. So I'm going to subtract 5 from both sides. Kill that. -2 sine theta is equal to 1. Divide out the -2. Simplify, these cancel. Sine of theta is equal to -1/2. All right. And we actually tackled these kind of problems when we talked about inverse functions. This is basically saying where on the unit circle is the y value, so where, comma, on the unit circle, is the y value equal to -1/2. All right. So having knowledge of the unit circle really helps, because if you don't have knowledge, at least on this level, and I mentioned this a few times, you have it available, you can look it up, but you still got to look it up. So here I'm on page 29. I'd have to flip all the way back to the early part of the unit in order to find my unit circle. But if you have good understanding of the unit circle, then you already know the answer, right? And so theta has to be equal to, well, it's a y value of 1/2 where sine is negative. Sine's negative in the third and fourth quadrants. So this is going to be the equivalent of 210 degrees and 330 degrees, but we need it in radians, right? By them giving the domain in this form, the answer, oop, that's weird. I'll leave it like that. Answers must be in radians. All right, answers must be in radians. All right. So yeah, I might know that it's 210 degrees, but I'd have to figure out the radian equivalent of that, which would be 7 pi over 6. And 11 pi over 6 would be 330 degrees. All right. Now, again, the calculator does some of this for you. The issue with, let's say if I wanted to do, because we talked about this also, if I want to get theta alone, I could find the arc sine of both sides. All right, so the arc sine of theta, arc sine of negative 1/2. All right, on the left-hand side, that would become theta, opposite operations, or we think about it when you compose a function with its inverse, you're left with the argument. Then I go to use the calculator to select, trying to get my fat fingers to work. It's really just not registered. Oh, there it is. All right, so negative 1/2. And it just tells you negative 30. All right. So negative 30. Now, you can just go into radian mode, repeat the calculation, and it'll say negative pi over 6, which is equivalent to 11 pi over 6. But from that, how are you getting the 7 pi over 6? You'd have to know that you're going backwards from 0 and also going backwards. Oh, actually, no, forwards from 180. That's not really obvious. So let me show you a better way to do it on the calculator. So we don't want this. This is bad news. You're going to run into trouble if you do it that way. All right, there are ways in which the inverse function is helpful for solving equations, and we'll tackle those in the next unit. But for now, we're just going to use, well, you could use a solver, or you could use a graph. I think most people are going to want to use a solver. So, I'm sorry, it's the equations app. They used to call it the solver. So, equations, hit OK, type in this new equation, right? In the original form, 2 sine. If I hit the X key, I can treat the X as the theta. If I do it a few times, it cycles through the different possibilities. So if you want it to feel like the problem on paper, then you might go with, just keep hitting this button over and over again until you cycle through to the theta. All right, so that's what I'll do. +5, shift pi, 4 sine, cycle through till we get a theta, +6. And then hit OK to lock it in. Go to solve equation, or solve the equation. It asks you where you want to solve, where you want to find answers. And trig functions are repeating cycles or periodic. So you could have many, many solutions. All I want are the ones that happen between 0 and 2 pi. So solve the equation. It tells me some numbers. Those numbers aren't in the nicest form, but at least we have something to help us verify our answer. All right. So if you type in 7 times the number pi over 6, you're going to get 3.665. Show you. All right. So it's not giving us the answer in the nicest form, but it's giving us the answer. So doing it again, 0 2 pi, solve the equation. And if you want, you could go right onto the number. And let's say this one is the one you want to verify, but you're worried that you're going to forget what the number was when you go to type in 11 pi over 6 on the home screen. Hit Shift var to copy it. Then go back into the main menu there, the calculation menu. Shift toolbox, and it'll paste it. So I don't have to write down the decimal. I could just port it over. So 11 pi divided by 6, same decimal. Well, the one I copied over is rounded, but still same idea. All right. So you could use the solver to get an idea of whether your answer is valid. And it also really, I mean, sometimes you don't even need help figuring out the n answer. It's nice to know how many answers there should be, right? By using the equations app, I can figure out that there's supposed to be 2 answers that I'm on the lookout for. All right, so that might lead me to my unit circle. Another type of problem that you could have involves powers of 2 specifically. This is in a quadratic form. If you're dealing with a quadratic, it could be the case where you just don't get nice numbers, right? Because sometimes, I mean, you remember quadratics, sometimes you got to use the quadratic formula to get your answer. And in those cases, you don't expect the answer to be very nice, right? But I'll show you how to handle that. All right, but first, if it's quadratic, we want to get everything over to the same side of the equation. All right, so I'm going to subtract the 5, subtract the 8 cosine of theta. They'll cancel on this side. So I'm subtracting, I'll do the 8 cosine theta first, and then subtract the 5, subtracting from both sides. So cosine squared theta minus 8 cosine theta minus 5 is equal to 0. And by the way, just for the first 2 examples, we haven't had to do anything with identities. It was just straight up algebra, but it is possible that you'll have to deal with identities along the way, and more than possible. I'm going to show you a couple of examples in a minute. All right. So when I go to factor this, since 5 is a prime number, the only possible factors of 5 would be 1 and 5, positive or negative. There's no way you're getting from that to an 8. All right. So this is not factorable. Use the quadratic formula. All right. So quadratic formula works in a very similar fashion. In ordinary algebra, it's x equals plus or minus the square root of, well, I forgot the negative b. Plus or minus the square root of b squared minus 4ac all over 2a. I got in the habit of doing the plus or minus stuff with the on the previous page, so it just zigged when I should have zagged. All right, but we get there. So ordinary algebra, the quadratic formula is this. For algebra involving trig, it's still the same right-hand side. All of this is still going to be the same, except the variable is not x. if this equation were x squared, so this equation, oh, my pen just kind of crapped out on me. Weird. It's sort of registering it, but oh, you know why? I need to get out of there. All right. So this equation, if it were x squared minus 8x minus 5 equals 0, then the ordinary algebra formula would work. Instead, it's cosine squared, then cosine. All right. So the quote unquote variable on the left-hand side would be cosine of theta. All right. So coefficients 1, -8, and 5. The 1 is my A value. The -8 is my B value. And the -5 is my C value. So cosine of theta is equal to -8. I'll backfill with all the values in a minute, but I'll read it out as I go. Then -8 squared minus 4 times 1 times -5 all over 2 times 1. All right, so the -8 goes here and here. The 1 and -5 go there and there, and a 1 over here. All right, so we'll simplify that. We're going to get two expressions. All right, we're going to get two expressions. We'll let the calculator do all the heavy lifting, though. All right, because remember, this calculator handles radicals very well. All right, so I'm going to create a fraction. Always populates it with an answer on top. Sometimes that's helpful, but most of the time I find it isn't. 8 minus the square root of -8 squared minus 4 times 1 times -5 all over 2 times 1. All right, so that's one variation of it. It's -8 plus or minus, so we'll have to do this a second time. Hit OK, and it gives us a simplified form, which is really nice. So I can say cosine of theta for one set of solutions is 4 minus rad 21. So then just do the same thing again with a plus sign, and you get 4 plus radical 21. All right. So what this gives us is at least a nice or relatively clean expression that represents the cosine of theta, but it could be either one of them. All right. And because in the unit circle, cosine is positive in 2 quadrants, the first and the fourth quadrant, we're going to have to kind of be careful with this. But here's an instance where I would use the inverse cosine. I would say cosine of theta is equal to the arc cosine of, I'm going to put it all together, 4 plus or minus rad 21. All right. So, oh, sorry, that would be theta is equal to. All right. So I'm just kind of like shorthand notation, sort of putting it all together. And that's good stuff. It's important. But once you realize that you're going to get a decimal answer, you may want to go over to the calculator to get an idea of how many answers you're going to get. All right. So that would get you right back to the original equation. Wipe this out, put this in. All right. It's going to be cosine. Hit the back arrow, square it. Theta equals 5 plus 8 cosine theta. Lock it in. Solve the equation going from 0 to 2 pi. And it tells me that I should be on the lookout for 2 answers. All right. So as long as I get 2 answers that are equivalent to what I see here, I'm good. All right. Another way to do it, which is probably say less popular, would be to graph this equation and see how many times it crosses the x-axis. All right, so you can do that too. All right, but I'll do the arc cosine. So alpha, not alpha. Hold on, force I have it. I don't know from what, but it just seemed like the right thing to say. So shift cosine, not alpha cosine, shift cosine, 4 minus rad 21. We want to be in radian form, so this is good. Calculator, I put it in the right mode. So 2.193 about. I believe that was one of the values that I saw in the equation app, radians. And then just do it again, this time with a plus. All right, this says non-real. So that means, and this is something I didn't really talk about too much in depth. There are circumstances where, and I know I addressed it, but it was one of those, like, in the course of a whole 5 minutes, talked about it very briefly. You could end up with a result like this, non-real, right? And that's because the arc cosine function has a particular requirement in terms of the domain, right? Whatever you put inside the arc cosine has to be between 0 and -1 and 1. All right. So that's really important to keep in mind. But for most people, it's sufficient to say, okay, I know sometimes I can get no solution. The problem is when I did the arc cosine with the minus sign, I got a solution, but I'm supposed to get 2 solutions. So just going back to the equations app, I don't love how it doesn't hang on to, I think it should hang on to your previous X min, X max, but just a thought. So I should be getting not only the 2.193, but I should get a 4.09 whatever, all right? So I got to sort of think about how that might happen. And it adds a layer of complexity to this. 2.193, if I were to plot that, here's 0, pi over 2, which is about 1.57, then pi, which we know is 3.14-ish, then 3 pi over 2, which so far isn't relevant, right? But, you know, decimal wise, it's 1.5 pi, so 1.5, 3.14. So it's going to be in the 5s, you know, 4s and 5s in that neck of the woods. I mean, it's between 3.14 and 6.28. So you slice that in the middle, so it's going to be in the 4s. All right. Let me just clean this. 2.193. I'm not sure where it would fall, but it's going to be in this quadrant somewhere. All right. Now the number for the 4 minus rad 21, that number is a negative number. So what we're saying is that we want answers that are in the quadrants where cosine is negative. All right. So that would be the second and the third quadrant. All right, that's where cosine is negative. So there must be another angle in this quadrant with the same reference angle, right? So this angle here was about 2.193. If I take pi and subtract from it about 2.193, I get 0.949, I'll say. That's my reference angle. The numbers are weird. They're ugly because we're in radian form, but more specifically, we're in radian form with non-nice answers. They're not like special unit circle values, right? But I do know that I have to have a 0.949 in this quadrant. So I just need to figure out what this whole angle going from here all the way around would have to be. I can do a better job of that, I think. So it'd be like going all the way around to get to this location. Well, once you get here, you're at pi. So pi plus 0.949. And that gets you to 4.0906 as the other answer. I'll just say equals. All right. So this is, in terms of equations, it's kind of, I'll say it's the trickiest kind, but only if you had to do it all out by hand. What I would say is get to this step here, or even just this step here, and then go use the equation app. You'll find how many answers you're supposed to get, and it'll tell you what those answers are, right? And if they're ugly like this, you know that it's not a matter of you looking at a unit circle to figure out your answer, right? So you can kind of, I'll say fudge it, I guess, but you know. The hope is that you come to understand the concept and then effectively utilize technology as you go. All right. Now, number 3, you see there's a disagreement between the trig functions. One is sine and the other is cosine. So I'm going to use a trig identity to get it all in terms of cosine. All right. Because I don't have a trig identity, a nice one, that'll change a cosine, just an ordinary cosine into a sine. But I do have a trig identity that'll swap out a sine squared for a cosine squared, right? So, and that is sine squared theta is equal to 1 minus cosine squared theta. So that's my sub. I can take this and put it in there and make my new equation 3 paren 1 minus cosine squared theta minus cosine theta equals 1. And by the way, you know, like I know number 2 is kind of a scary problem. Everything else is easy in comparison, right? In comparison, you look at number 1, we did a lot of writing for that too. And number 3, we're already off like, oh, we got to use an identity. But it's not going to be as complicated because you can reference the unit circle for a problem like this. All right, so distributive property, 3 minus 3 cosine squared theta minus cosine theta is equal to 1. Move some things around. We want it to be in descending order. So I'm going to subtract a 1 from both sides and then rewrite. All right, so I'm going to shrink this down. It's like shrinky dinks when if you ever played with the shrinky dinks back in the day, it looked hideous when it was large size, but it looked a little nicer when you shrunk it down. I wish that were the case for this. It still looks pretty bad. Bad looks really bad, as in bad is the word of the day. All right, BAD, bad. Not good, but bad. First word of the day. All right, so this cancels over here. I'm going to have a negative 3 cosine squared theta. That's coming from here. Minus cosine theta coming from there. Plus 2, which is coming from here. That looks terrible. Nope, it's not going to look good. All right, best I can do. All right, so now we have a nice uniform, in terms of the trig function, a uniform trig equation. I'm not in love with having a leading coefficient that's negative, so I'm going to negate the whole equation. 3 cosine squared theta plus cosine theta minus 2 is equal to 0. So I want to factor. I'm going to kind of imagine it's 3x squared plus x minus 2. So to start off, it would be 3x and x. I'm going to make it 3 cosine theta and cosine theta. I want a product of negative 2. But if I put the 2 here, that's going to make this a 6. That's not helpful. So I'll put the 2 here and put a 1 here. All right. If the 3, the product of 3 of the outers and the product of the inners gives a 2, if the 3 is positive and the 2 is negative, that'll get us our middle coefficient of 1, the understood 1. All right, that's what we get if we add these two together. So I want this number to be positive and this number to be negative. All right, so I could take my two factors, 3 cosine theta minus 2, set that equal to 0, cosine theta plus 1, set that equal to 0. I'll get cosine of theta is equal to 2/3. Cosine of theta is equal to -1. The only time cosine is equal to -1 in the unit circle is when theta is equal to pi. All right, so that part's at least accounted for. The cosine of theta equals 2/3. Well, 2/3 is not one of our special angles. All right, so again, this is what I'm saying. If it's not, sorry, not special angle, special ratio. If you come against something that's not one of your special ratios, you might want to use the equation app, right? Or you could also, I mean, you can give it a shot by doing arc cosine of 2/3, but you get that number, and that number is just a reference angle. So you would end up having to do the same stuff that we did over here, which I can't imagine people like really too much. So for this part only, I would go into my equation solver and then throw in just this equation. All right, so get rid of this, not back to the original one, this simplified one, and write cosine theta equals 2/3. Solve it. Again, 0 to 2 pi. And so we got the 0.841 that the calculator in the calculation menu gave us, but we would have had to work to find the 5.44. So we'll just take it. We'll just take it from the calculator. So 0.841 and 5.442. All right, these are all in radians. All right, so one clean, two of them not so much, but still a lot easier than number 2 because we don't have to worry about the quadratic formula. If something's factorable, you could just go after it, using a factoring approach. That being said, because the answers ultimately ended up being ugly, you think back to when you learned about factoring and completing the square and quadratic formula, maybe you're like, I know I can factor, but I don't want to because it's complicated. Maybe you're not as proficient at it as you'd like to be, but you could do it if you really knuckle down and tried to do it. But you're like, quadratic formula is much easier. I'm going to do it that way. Right? So you could go either way. Again, it's not an algebra course. I'm only showing you algebraic techniques because in a lot of cases, it saves you from a lot of calculator work that you would not otherwise have to do, or would otherwise have to do. All right. So speaking of which, number 4 is actually very easy to do without a calculator, as long as you have access to the unit circle or know your unit circle. So this is a quadratic in binomial form. So add 1, sine squared theta is equal to 1. You want to take the square root, or you want to take the square root to get rid of that power of 2. So we apply it to both sides. Then we get sine of theta is equal to, well, the square root of 1 could be positive or negative. So that means I'm looking at sine theta could be equal to -1. Sine theta could be equal to +1. So I would just be asking myself, where on the unit circle is the y value equal to -1? Only happens in one place. 3 pi over 2. Where on the unit circle is the y value equal to +1? Only happens one place, pi over 2. So, in comparison to all the stuff we had to write here, this is like 3 steps. All right. The last one that we're going to do, because like I said, we're not going to really bother with tangent. We'll pick that up in the next unit. Number 5 has a little bit of a quirk to it, but that's where the equation app can be really helpful, because again, like I was saying before, sometimes all you really need to know is how many answers there are, right? Because then you could figure out, okay, if I know how many I'm looking for, once I find that number, then I know I'm good, right? So I'm going to apply an identity, and that is 1 over cosine theta is equal to secant. All right. Now I have to make a little note here. It's a domain consideration. Cosine of theta cannot be equal to 0. All right. Otherwise, the equation will be undefined. It all starts coming together because we talked about that with rational functions. So think of this as a trig version of a rational function. All right. Now that I've established my domain consideration, I don't want cosine theta to ever be equal to 0. I can solve this equation. If I get to a point where cosine theta is equal to 0, I will dismiss that. All right. What I'm going to do is multiply both sides by cosine of theta. On the left, it becomes 2 cosine squared theta plus cosine theta is equal to, and on the right, it becomes a 1. All right, these are equations, not identities. We're not trying to verify the 2 cosine plus 1 is equal to secant. We're trying to solve for theta. So now we do have license to cross the equal sign. We can multiply both sides by something, divide. I should have mentioned that earlier, but like that's how it works with equations. All right, subtract 1 from both sides. 2 cosine squared theta plus cosine theta minus 1 is equal to 0. Factor it if it's factorable. All right, so 2 sets of parentheses. To get to 2 cosine theta, 2 cosine squared theta, we would need to have 2 cosine theta multiplied by another cosine theta. To get to a 1, it has to be 1 or 1. My outer product, 2 cosine theta. My inner product, 1 cosine theta. We only really care about the coefficients, though. If I want to get a result, when I add these two together, all right, so when I add these two things together, if I want to get a result of 1 cosine theta, the 2 has to be positive, the 1 has to be negative. All right, the product of 2. The way the product of 2 will be positive is if this number is positive. The way the product of 1 is negative, 1 cosine theta, if we want that to be negative, this has to be negative. So 2 cosine theta minus 1 equals 0. Cosine theta plus 1 is equal to 0. Solve these two. They're trigonometric equations in a linear form. Form, F-O-R-M, form. Second word of the day, form. Like trigonometric form or linear form. All right, so I'm going to add 1 to both sides. 2 cosine theta is equal to 1. I'll also subtract 1 from both sides over here. Not much going on with that one, which is good. You get cosine theta is equal to -1. Divide both sides by 2 here. which means cosine theta has to be equal to 1/2. Cosine theta is equal to 1/2. It's also equal to a -1, all of which are nice unit circle ratios. All right, this looks almost like a negative sign or a minus sign, so I'm going to fix that. In the unit circle, cosine is equal to 1/2. Cosine theta is equal to 1/2 when theta, so that's the x value at any coordinate, when theta is pi over 3 or 5 pi over 3. Cosine theta is equal to -1 only when theta is equal to pi. All right. Now, kind of looks like black magic. I'm just pulling these radian measures out of thin air. No, it's I know the unit circle. All right. So these are the values that you would get if you looked at the unit circle, looked for any instance in which the x value was 1/2. You'd see that happens at a radian measure of pi over 3. And any instance in which the x value, the x value is equal to -1, that would be only at pi. And like I said, we'll table number 6 until the next unit. But I did want to go back and tackle one or two of those identities, right? Just to kind of bring it back together with what we had been doing. All right. Maybe I'll just do one on each page. And I'll make sure the solutions for the other ones are up there, just so you have it. All right. And also, while I'm trying to stall for time here, because I got to imagine somebody's still looking at the solution. The practice test, that's been posted for a couple of days now, a few days. Something to be mindful of is for the feedback for the questions, like after you submit, it asks you, or, it does a double check on your solutions to say, like, okay, you got this one right, you got this one wrong. The correct answers are listed as Desmos links, right? So when you click on that link, it'll bring you to, in some cases, they're handwritten solutions. Other cases, I just type them in. But the solutions to the non-multiple choice questions are there as Desmos links. All right, so you could use that to kind of guide your studying. All right, so let's go on back. Let's look at page 26. Definitely, I think number 9 is probably more beneficial because we've done stuff like number 10. So for this is trig identity verification, not solving trig equations. So this is the instance where we create the impenetrable barrier and work one side independently from the other and see if we can get them to be equal. All right. Anytime I give trig identity verification problems, they always work out. So it's just a question of, perseverance. All right. So impenetrable barrier, start with the more complicated side, which I think is the left-hand side. Hopefully you agree. One of the strategies was to change anything that was not sine or cosine into an expression that it is or involves a sine or cosine. So the cosecant is 1 over sine theta. I'm sorry, I'm in a theta habit now from all those trig equations. 1 over sine x plus cotangent is cosine x over sine x. Tangent is sine x over cosine x. And sine x is just sine x. All right. But I'm going to write that as sine x over 1. All right, because we have a common denominator for the top, but we can get a common denominator for the bottom. All right, so for the bottom of this complex fraction, so like I said, I don't want to rush this too much. If this already has a common denominator, I'm not going to worry about it. The bottom one I want a cosine on the bottom rather than a 1. So I'm going to multiply top and bottom of my second fraction by cosine x. All right. So when we combine the numerator of this, that's going to become 1 plus cosine x over sine x. The bottom is going to be sine x cosine x. Oh, sorry. Jumped the gun. Now my thing is jammed up on me again. It is possible that it's just dead. No, it's still registering. Is it the whole screen? No, it's not the whole screen. It's just the Apple Pencil. All right, I'm going to call timeout for a sec. Resume recording. All right, so get rid of this. It was supposed to be sine. Oh, whoa, it defaulted, didn't it? It's not what I wanted. All right, so it should be sine x plus cosine x sine x. All over cosine x. All right. Now, our goal here is to simplify as much as we can. At first glance, you might look at this and say, I don't think I can do anything. But there is, in this expression now, a common factor, a GCF. All right, the GCF would be sine of x. So I'm going to leave the top the way it is for now. The bottom, I'm going to factor out a sine of x. And in doing so, if I divide each of these terms by sine of x, I'm going to get 1 plus cosine of x. And on the bottom, just cosine x. Now, if you're comfortable with complex fractions, you might know precisely what to do here, but I'm going to assume that maybe you don't want to do it that way. So what I'm going to do is keep, change, flip. Keep, change, flip. Some people say keep, change, change. You're dividing two fractions. Keep the first fraction the way it is, multiplied by the reciprocal of the second one. So that's going to be 1 plus cosine x over sine x times cosine x over, so I'm flipping this one, sine x 1 plus cosine x. All right. We always want to take a little peek at what you're going for. Doesn't look like we're getting there, but we are. If we put these two fractions together, it's going to start to shape up. But we have two fractions. In those two fractions, one of the numerators is 1 plus cosine x. One factor in the denominator is 1 plus cosine x. So those will cancel. It always cancel like factors top and bottom of a fraction. Okay, so that's kind of nice. So the part that was making it ugly is actually gone. That first fraction is now it's going to become a 1 over the sine of x. The second fraction becomes cosine x over sine of x. Now, if we peek at what we were looking for, cotangent, cosecant. Well, 1 plus sine x is cosecant. Cosine over sine is cotangent. And we just write it in the form that they have it on the other side, cotangent x, cosecant x. All right. So a little on the tricky side, a lot of stuff going on with this one, but it's all rooted in, I would say, basic trig identities. but mostly algebra. Because really you think about it as like, what step did we do the trig? That was all right here. The trig stuff was done after that step. After that, it was just algebra. Until we got down here, then we did a little bit of baby trig after that. Right. So I'll do one more. I'll do one on the next page, one that involves a double angle identity, or some and difference identity, some and or difference identity. Right. So let's take a look. Number 6. Number 6 is a good one. So this says secant of 2x is equal to secant squared over 2 minus secant squared. All right. Well, the first thing I'm going to do is I'm going to change the secant squared, secant of 2x. So I'll make my impenetrable barrier. The reciprocal of secant is cosine. So this is equivalent to 1 over cosine of 2x. All right. Just to kind of make it a little bit more obvious what I'm looking for. All right. Because the odds of us getting from here to here, they're not as good as getting from here to here. All right. So now that I have that on the left, I'm just going to leave it alone for a little bit and go to the right. The helpful hint is to take anything that is not sine or cosine and make it sine or cosine. Now, there are rules that'll allow you to go from secant squared to another type of trig function. All right. In particular, a tangent function. But if we want to get ultimately this, I want to convert these secants into cosines. So 1 over cosine squared x. All right. Now, my lousy handwriting aside, you have to remember that cosine 2x and cosine squared x are not the same thing. All right. So if you got to be a little bit more precise with how you write things, like I'm trying to do, it's probably not the worst idea in the world. All right. So on the bottom here, I have a number minus a fraction. So I'm spacing it out because I'm about to get a common denominator. All right. So I'll have to multiply top and bottom. Now that 2 is really a 2 over 1. I'm going to multiply top and bottom by cosine squared x. All right. So I'm going to leave the top alone, 1 over cosine squared x. On the bottom, I'm going to have 2 cosine squared x minus 1 all over cosine squared x. And this kind of problem, I'll tell you, is a whole lot easier to handle if you familiarize yourself with the rules. All right, the trig identities on page 23. Because sometimes you don't know that what you're looking for is staring you right in the face. All right, but I'll take it another couple of steps. So keep change flip. 1 over cosine squared x times cosine squared x over 2 cosine squared x minus 1. Little algebra, and cancel the cosine squared x's, and you're left with 1 over 2 cosine squared x minus 1. Now, if you familiarize yourself with the rules, you would recognize that that is one of the double angle rules for cosine. All right. If you don't, then you get to this step and say, well, the only thing that differs between the left side and the right side are those two denominators. So if I had to make an educated guess, I'm going to guess that this is equal to cosine 2x. Because that's the only way it could work out. And since I already mentioned that every problem I give you is going to work out, that must be a true sentence. But for confirmation, you go back to the rules page, double angle rules for cosine. Right here, that's the relevant one. There's 3 versions of the cosine of 2a. The one that applies in this problem is the 2 cosine squared a minus 1. All right. So once I get that as the sole member, I guess, of the bottom of the fraction, then I know that I can replace it with a cosine 2a, which happens to be the other side of the equation, or the identity. All right. So we have our proof, left equals right, and we're good to go. All right. So like I mentioned, I'll put solutions to the other couple of problems up. I'll put it in the class notebook. Let me stop the recording.